One clear night, Qubit climbed onto a safe terrace, looked up, and nearly dropped his binoculars. The stars were sparkling like 1,000 tiny diyas at a sky party. One winked blue, another flashed red, and a bright one seemed to dance. Are they switching themselves on and off? He wondered. Lovely guess, Qubit, but stars do not blink like bulbs. A star is an enormous, distant ball of hot glowing gas, sending light steadily in every direction. Over a few seconds, its real brightness usually changes very little. The rapid sparkle we see is mostly added much closer to home. For almost the whole journey from a star, its light crosses the near empty vacuum of space. There is no thick, restless air there to jumble the beam, so the light travels smoothly. Then, during the final thin slice of its enormous voyage, it meets Earth's atmosphere, and the quiet beam enters a moving obstacle course. Our atmosphere is a deep ocean of gases held around Earth by gravity. It is not one perfectly even sheet. Some patches are warmer, some cooler, some denser, and some thinner. Winds continually slide, mix, stretch, and tumble these patches, even on a night that feels calm beside your window. Light changes speed slightly when it moves through materials of different optical density, so its path can bend. This bending is called refraction. You have seen a related effect when a straw in a glass of water appears bent. In the atmosphere, the changes are gentler, but starlight crosses many shifting boundaries one after another. Imagine thousands of invisible, wobbly lenses floating overhead. Each moving pocket of air bends the arriving starlight by a tiny amount. A moment later, the pockets have changed position and shape, so they bend it differently. The beam reaching your eye keeps wandering, squeezing, spreading, and changing direction many times each second. A distant star is so far away that even a giant star appears to us as almost a single point of light. When turbulent air nudges that narrow point-like beam, the star's apparent position dances slightly. When the air briefly focuses more or less light towards your eye, the star also seems brighter or dimmer. That rapid change in apparent brightness and position is called stellar scintillation. We usually call it twinkling. The star itself has not bounced around. The final part of its light path has. Qubit's sky disco is really a fast record of restless air moving between the star and the observer. What about those tiny color flashes? Different colors of light bend by slightly different amounts, a little like light passing through a prism. Strong turbulence can separate the colors for an instant, so a bright star may sparkle red, blue, green, or white. The star has not suddenly changed its paint job. Stars often twinkle more near the horizon. Their light then travels through a longer slanting route across the atmosphere than when the star is high overhead. More air means more moving pockets and more chances for bending. Dust and haze can add extra dimming, although turbulence is what drives the rapid twinkle. Now Qubit spotted a bright planet and frowned. It looked steadier. Planets are much closer than stars, so through a telescope they have tiny disks rather than point-like images. Light arrives from many parts of that little disk, and the atmosphere bends each part in slightly different ways at the same moment. Those many variations tend to average one another out, making a planet's total light look steadier to the naked eye. But this is a useful clue, not an unbreakable rule. A planet low near the horizon, or viewed through very turbulent air, can twinkle too. No celestial object has signed a no-twinkling promise. Astronomers call the atmosphere's blurring and dancing effect seeing. Poor seeing can make a telescope image wobble like jelly, hiding fine details and smearing close stars together. That is why many observatories sit on high, dry mountains above a large share of the thick, dusty, churning air near the ground. Inside a modern observatory, instruments can measure how a reference star's image is being distorted. A computer rapidly adjusts a flexible mirror to cancel much of that distortion, many times per second. This technique, called adaptive optics, helps ground-based telescopes produce much sharper images. It is like giving the telescope lightning-fast corrective spectacles. Another solution is to put a telescope above the atmosphere. In space, there are no shifting air pockets around the telescope, so stars do not twinkle for that reason. Their images can stay remarkably steady and sharp. Astronauts looking through a spacecraft window may still see motion caused by the spacecraft or their own eyes. Twinkling can even reveal information about the air. By measuring the speed and strength of scintillation, scientists can study turbulence in different atmospheric layers. Radio signals from spacecraft can also flicker while crossing charged regions high above Earth, though that is a related signal effect, not quite the same visible star sparkle. So, can you identify every star just because it twinkles? Not perfectly. Bright stars may twinkle strongly, planets may twinkle in rough air, and haze changes what you see. A sky map or astronomy app used with an adult is more reliable. Still, spotting steady and sparkly lights is a brilliant way to begin observing. Here is Qubit's starry recap. Stars usually shine steadily, but their point-like light crosses moving pockets of warm and cool air. Refraction makes the beam wander and change brightness, so our eyes see a twinkle. Planets usually look steadier, space telescopes escape the shimmer, and Earth's atmosphere gets the final sparkling bow.